All right, so today we welcome José Ferreira from New our group, which is going to basically tell us about cosmological tests on non-metricity with the modified theories of gravity, or theories of gravity in general. Okay. And yeah, please start with everyone.
Thank you. Hello, everyone. Good morning. I just joined for the PhD here at Aveiro. And today I'm going to speak to you about the work which I have developed beforehand, which I entitled Cosmological Tests on Metricity-Based Theories of Gravity. This was done with Nelson and Aveiro, which were my supervisors, and also with Demos. In case you're interested, this work can essentially be summarized. Okay, so here is the outline for this presentation. Let me start by making a brief introduction. Sorry. Okay, so let us start by making a brief introduction. So, in order to encompass the evolution of the universe theory, the standard model of cosmology, also referred to as non-metricity, has been under development in the last few decades. This model, which remains fairly simple in its theoretical formulation, assumes that the universe at this scale can be accurately described by the theory of general relativity. It also assumes that the universe is permeated by a perfect fluid, which is composed of three different types. So we have matter, which is composed of essentially ordinary and dark matter. We have radiation, both photons and neutrinos, and also this strange new component that we call dark energy. Additionally, it assumes that the universe at this scale is spatially flat, homogeneous, and isotropic, which is mathematically described by the flat FLRW metric, where this A of t is the scale factor of the universe. The last ingredient in this cosmic recipe is initially period of initial inflation, and voila, we have the whole non-CDM. Although it remains fairly simple, considering the amount of things that we're trying to describe, it can accurately describe most phenomena which is observed at large scales. So, namely, the cosmic microwave background, the accelerated expansion of the universe that we observe today, and the large-scale distribution of galaxies. However, despite of its successes, it is currently facing some challenges, of which the most well-known are the Hubble tension, which is the tension in the measurement of the Hubble constant, when taking into account either low redshift or high redshift observables. There is also the lack of theoretical explanation and measurement laboratory of the dark sector, so both dark matter and dark energy are still a mystery to us. And there's also a few anisotropies in the CMB, which are a little bit hard to explain. This means that one should probably look beyond the standard model of cosmology in hope of finding an explanation to these previous issues and many others which plague the this field. Historically, there have been no shortage of attempts in replacing lambda CDM or general relativity. From theories of gravity that rely on higher dimensions, new types of fields, coupling between the different fields, etc. There's a whole lot of things to take into account. In this work, we'll be working, in this presentation, I'll be speaking about a recent entry to this roadmap, which isn't shown here, which is called F of Q theories of gravity. In F of Q theories of gravity, we replace the very well-known Ricci scalar in the Einstein-Hilbert action by an arbitrary function of the non-metricity scalar, which is called Q. Sorry? I have the credits in the end, but I can check it. Well, I was just curious. Okay, sorry. I avoid putting references sometimes because it feels like a little bit of a blur. It's an URL, it's not a company. But I have the references too. Okay, so before we go into the details of this FOQ series of gravity, I'll be introducing gravity as a geometrical theory and motivate how that can be used to create modified theories of gravity. So it is well known that we can decompose the affine connection in a sum of three different contributions. So the first is the Levi-Civita connection, the standard Levi-Civita connection, which depends on the metric and its derivatives. We also have the contortion that itself depends on the torsion, which encodes the failure of the metric, the connection in being symmetric. And finally, we have the disformation that includes all contributions coming from non-metricity, where non-metricity is as usual defined by the covariance derivative of the metric test. Using this decomposition, we can then take the generalized Riemann tensor and rewrite it in the following way. where you can see that this generalized Riemann tensor is equal to the usual Riemann tensor, where the LC on top denotes a quantity that only depends on the Levy-Civita connection, plus some extra terms that all depend on this tensor M. This tensor M is defined as the sum of both the contortion and the deformation together, meaning that it includes all contributions coming from both non-metricity and torsion. If we set non-metricity and torsion to 0, contortion and the deformation will be 0, this M will be 0, and all we have is essentially this first term. We have the usual Riemann tensor that we find in the theory of general relativity. We can then use these three geometrical entities to create three scalar quantities that can be used to create geometrical theories of gravity. If we now create a theory of gravity in which we rely on the Ricci scalar, which only includes curvature, that is just GR, or if we create a theory of gravity which only uses the non-metricity scalar in the action, or only the torsion scalar, it is interesting to note that what happens is that we have three equivalent theories of gravity. This equivalence is sometimes referred to as the geometrical trinity of gravity. However, because we wish to look for modified theories of gravity, we must modify the action in such a way that it diverges from GR. Perhaps the simplest approach one can take is to take the scalar quantities in the action and generalize them to an arbitrary function of themselves, right? So this leaves us with the widely studied class of f of r theories of gravity, also f of t theories of gravity, and of interest to this work, f of q theories of gravity. It is important to note that in this generalized setting, there is no longer a necessary equivalence between f of r, f of t, q, and f of t, although it might happen, as we'll see further ahead, for specific metrics. Another relevant point which I'd like to highlight is that if we set f of r equal to r, or f of q equals to q, or f of t equals to t, then we essentially fall back to the geometrical trinity of gravity, and what we have is once again the theory of general relativity.
Yes. In the case of f of r, that's of course not the general even for dimensional theory, right down just on curvature invariance. We have Ricci squared and Riemann squared. So I guess that means other formulations of these Euler applies. Is that true?
Can you repeat the question, please?
Right. So you would have, instead of just a theory that's an f of r, you would have something that depends also on the Ricci tensor squared.
Yes.
Right. So that's not the most general theory of gravity, right? And in fact, some people debate is kind of something that justifiable to include from a detective theory viewpoint, higher dimensional objects, but not all of them. But there's an equivalence, of course, with scalar tensor theories, which is very particular to f of r models. So I was wondering about these two other models, f of q and f of t. If a similar statement applies, you can build other variants of these basic quantities and build more general theories of gravity. So what's the status there? Is there a similar statement that this f of q based on a scalar invariant q is not the most generic theory of gravity that uses non-metricity or the case of torsion, in the same way that f of r is not the most generic theory of gravity that you can write down? So that was it.
Yes. I remember specifically it's a work by Professor Precision Blow, in which he considered non-metricity and he didn't consider the trace of the energy moment. It's not something that
that's slightly different because that's the energy momentum, that's not a geometrical quantity. So
I think you can miss objects, but I've never seen anybody.
Okay, so we can do that. Okay, thanks. Well, we can discuss more.
So, okay, right. Now, what does gravity look like? If we are to vary the action with respect to the metric tensor, as usual, we, instead of obtaining the usual Einstein field equations, we obtain a set of modified field equations where the argument q was derived for simplicity, and this index q it denotes the derivative with respect to the non-metricity scale. This tensor p is simply called the non-metricity conjugate, which is defined as follows. And then, due to the lack of curvature and torsion in the connection, we are provided with an additional gauge frequency. The gauge that we've picked is a special gauge, and it's called the coincident gauge, and allows to set a vanishing connection for all spacetime, not just blue. Additionally, unlike some of the modified theories of gravity that people are working with, especially the ones related to the gravitational sector with the matter sector, there is a conservation of the stress energy momentum tensor in this theory. Okay, so here's an image which I like to show that I believe provides some intuition behind the behavior of each of two metrical objects at play. So we have curvature, which essentially causes the rotation of a vector when it's propagated in parallel. We have torsion, which causes the non-closure of a parallelogram. And then non-metricity, which essentially changes the length of a vector as it's moved along its path. Okay, so moving on to cosmology in FFQ, I will be speaking about the assumptions that we'll be making regarding our FFQ cosmology models.
Sorry. Okay, yeah, so of course that's the geometric picture, that's fine. So, but there's ideas also physical picture. So when we think about curvature in terms of gravity theory, we think about forces, and we say, okay, how do you explain it? You tell people about the radiation equation of the curvature, the Riemann tensor is here in this way, and it's telling you how kind of forces behave. So that's a very physical thing. So how do you think about the torsion and the non-metricity in terms of the physical? You told us that they can, in the simplest case, they are kind of equivalent. But how do you think in terms? Because this is gravity, trying to describe gravity. So this torsion thing, how is it? What's your physical thinking about it? And the non-metricity? Do you have one?
No, that's what bothers me.
Yeah, I'd like to know
because it's weird. I've asked a few people, for example, what is the planet something like that to provide some physical information on what's at play. Because as you said, I'm not quite sure where the distortion is. They argue mathematically that it can be used to create three equivalent theories. Okay, sure. But what physical intuition is there behind each of these geometrical objects? I don't know.
So let's say that you consider a theory, let's say a torsion or something. Can this be mapped to a theory without torsion, but with some extra fields that could be a scalar fields or vector fields or something like this?
I don't know. I'm not certain. But I remember seeing people speak about that as far as I know. There are some situations where you actually have a mapping between FFT and FFQ, for example, which we'll see a little bit further ahead for specific metrics. So we have a given metric, and then suddenly what FFT and FFQ are very similar to each other. There's a reason behind it. But whether there is a complete mapping between them, I don't know.
So they say here's a string response, uniform potential, and that can be thought of as torsion. So these can map that into a matter field. So this is uniform potential. At least in some cases, this is true. You can simply rewrite vector torsion as a particular type of antisymmetric field potential. Because I think it's a generic thing. And you can look it up because people will describe this.
Maybe I'll skip the question.
We haven't looked into that. Generally speaking, I remember I saw. What I saw? I remember there were issues because if you have non-metricity, then the length of the vector changes, so it affects geodetics. And I tried to figure out how it would work because now, for example, if you want to make some statement of general relativity, you need non-metricity. Right? And if they say they have a non-metric theory which is completely equivalent to GR, then how do you map one thing to the other? But I'm not sure. So our approach is mostly on a cosmological scale mainly because then we can get rid of all these things.
But in these models, this is kind of discussion, so we can give you more time at the end. Okay. But in these models, is it then postulate that really important particles still follow geodesics, like the GR, and even though the metric might not be currently observed or it might not be symmetric. So I mean, this is very important, right? So one of the things that some people sometimes say about torsion is a part of the connection. So in GR, we think of connection, which is a non-tensorial quantity as gravitational force, and you want to gauge it away in a free-falling frame. That's only possible because it's non-tensorial. But torsion is the tensorial part of the connection. It doesn't go away in the freely falling frame if it's there. So it kind of seems to clash a bit with the equivalence principle in this. So I don't know what it means really.
Something I'm not understanding. So you're saying that you have this finity, so they're equivalent, right? But this is
Only for our cube.
yeah.
Not for the general.
When you say that they are equivalent, are you probably the same motion? Because it seems that they have different physics.
It seems that's one of the things that bothers me. But once again, exactly.
So when you say that they're equivalent, what do you mean?
I mean that physically they're equivalent. So the behavior should be the same. So if you have an R or a Q or a T in the action, then the physics that you measure should be the same. Go to the solar system, you do something.
But I think that's what you're saying is that you recover the field equations and how there's a mapping between the field equations and the three models, right?
Yes.
But you get, so then you have to say something about the motion of test particles, point particles. Is it still equivalent in that respect? I mean, what you postulate? You still postulate, that particles follow geodesics.
So, that's it. Because the claim is already advanced and that you can think of space we normally think of it just which would be R and space without torsion and which is but instead you can have just flat space but with torsion.
Yes.
So, and you can recover you can map one to the other. This is the thing.
Yes. The argument that they did on this paper was purely based on the action. So they used this generalized Riemann tensor, and what they did was if they were to set two of them to zero, then you have the third one, and they show that from an action point of view they were equal. They diverge by some extra boundary terms, but because the integral is overall spaced out as boundary terms.
You are mapping one space time to another, right? Not necessarily these quantities inside of this space time.
They're mapping field equations in a sense. They're not mapping space
I
time.
need to say what you would have.
What's the fixed
Yeah,
point?
exactly. How do you map the point, right? So how do you map the geodesics in
Yes,
space
yes.
to the evolution in
Yeah.
a flat space with torsion, right?
I also I don't know if I ask myself, and it seems to be
Yeah.
a little bit hard to understand.
It's not. It's kind of not completely, trivial to me at least that you can map a formulation in terms of pure torsion to a formulation in terms of pure curvature or the other one, which is something else. Although I think that thinking about GRS and physics of flat space-time is not kind of novel refinements of physics about very non-linear speed to on flat space-time. That's a perspective, but this is purely geometric in the terms of another quantity. So it seems to be non-trivial. But does this really encompass a total mapping of the physics of GR into this here? That's not clear.
I suppose the correct question for me to avoid getting issues in the
But it's a dangerous thing to put your life in the hands of somebody.
But I don't completely understand.
No, but this is.
Sorry.
Does it hold
the vacuum or generic strings on the tables? So for any matter
I would assume that it would be true for because if the field equations are the same, they are obviously the same. It shouldn't be just one vector. But I have to say that I've looked it up. Okay, so let us carry on. Exactly. So as for cosmological assumptions, we are assuming, as usual, especially flat homogeneous and propagated. Once again, flat hyperlogarithmic method where any of these are scale factor. And then we also assume that each component of our fluid can be described by a using the continuity equation, which comes out of the conservation of the stress energy momentum tensor, and assuming this simple parameterization, we can then obtain the scale for each component. So we have radiation, matter, and organic. Essentially, so far, everything is equal to the CDF. We've made no changes whatsoever. So, in what, where does it change? Because we don't have these standardized field equations. When we introduce our cosmological assumptions, we get a modified first treatment equation instead of the usual, where h is simply a Hubble function, which is the time derivative of the scale factor as divided by the scale factor. There's also a very interesting remark to make, which is regardless of the cosmological model that we are considering, there's this relationship between the non-metricity scalar Q and the Hubble function, which holds true at all times. And as I hinted at before, in a flat FLRW spacetime, both f of q and f of t have exactly the same field equations. So this means that in this setting only, the behavior both at the background and at the derivative level of both f of q and f of t are exactly the same.
So f here is your function of
It's our function. Yes, we're working with the generalized model. We can do whatever.
So should we cover the equal one? F of q, just q, right?
Exactly.
Then
if you look at this modified first Riemann equation and if you do the maths, if you set f of q equals to q, then you will recover this the first Riemann equation. So if we set f of q equals to q at the cosmological level,
Subscript is a derivative.
yes, the exactly. So maths check out this for this case.
Should I think in terms of field equations instead of doing capital maths? How should I think in terms of field equations? This perspective of this geometrical trees.
The field equations, at the cosmological level or at the
Just the Einstein equations.
just the Einstein equations? How should you think about them?
Is that they're exactly the same?
No. In this case, for f of q, not necessarily, because we only if you set f of q equals to q, do we fall back to the equation where we have the
geometry. So when we use trigonometric answers, it's because it shows that assuming that's all the homogeneity, that's the most generic. But is it shown? Because now we have the possibility of non-symmetric metrics. That to me opens a little bit of a paradox in terms of what it means. So, I mean, how is the study of isometries and the conclusion that indeed the line element, you're using it as an answer, that's fine. But I'm going a little bit beyond and asking, is it true that this sort of answers, the trigonometry law, is still the most generic one that's compatible with the assumptions of homogeneity and assumption? Is it? That's my question. Has it been shown that? I don't know. I'm asking.
Me neither.
Okay.
I never thought about that.
Right. So, because at least in the case of a non-symmetric metric, it seems to me a bit, what it means, and therefore the different degrees of freedom we can communicate, how they could impact on this sort of question. No, I think you recover the equations of motion. That's a further constraint. So you're imposing kinematic constraint.
Right.
Kinematic constraint that you have certain symmetries, and that means, there's a set of Killing vector fields and so on. I don't even know in that case if that goes through the analysis of what is.
No, but this is the same thing.
Well, it's a dynamical. I think that the mapping is a dynamical one. See the difference? You're saying that the field equations can be mapped into three formulations. Now we are talking about the kinematic thing, which is what does a symmetry mean in this kind of setting?
Right.
So what's a Killing vector? What does it mean to have a maximal symmetry group of a spatial section? It's a metric G, which is non-symmetric, which has further degrees of freedom. So the point is, the answer, it was non-trivial. So when Friedman calculated these solutions, he didn't know it was the most general thing. Then, in the 30s, going back to history, then Robertson and Walker, they wrote the paper and they showed mathematically that indeed, and we now do it in the GR course. But if you change the sort of geometric structure of your theory, what does, this kind of spatial equality mean of, isotropy and homogeneity? Does it mean that you must have a metric of that form? Could you excite some of the non-symmetric, non-diagonal degrees of freedom and it's still compatible? So it's not clear to me. I think that my impression is that this is a sort of game that one is playing in terms of having new field equations and deriving solutions, but the fundamental geometric questions are deep if you go into this, and I'm not sure how much they were explored. So that is the question. But we are discussing. I mean, it's just you're just discussing, raising questions.
Yeah, okay. Let's move see further ahead. One of the pros that we're using to test this cosmological models are essentially the gravitational waves. So we have to know how does having this cosmological model modify the propagation at large scales. As usually consider that a gravitational wave can be taken as perturbation as locally flat space-time. And in London CDM, the propagations for the modes of the gravitational waves have the following equation of motion, which corresponds to luminosity distance for the gravitational waves, which is equal to the standard luminosity distance function that can be defined in the following way, where h is once again our Hubble function, and z is simply the cosmological redshift that can be scale five. However, in f of q, this equation is modified by an extra friction term, delta, which takes the following form. Which in turn causes a modification to the luminosity distance of gravitational wave, which takes the following expression, where the luminosity distance, the ELZ, is again the luminosity distance function, and we have this extra term right here, where the index naught denotes the value of the quantity as measured. So this extra term right here will be the key that will give you the cosmology and we'll see the apart. Okay, so moving on to the observables that we use throughout our study. The first one, which I'd like to speak to you about, is type 1a supernova. The type 1a supernova, its apparent magnitude can be obtained by the following equation, where MOBS is the apparent magnitude. The large M is the volumetric magnitude for the type 1a supernova, which is a measure of the total radiation across all wavelengths. And then all we have is the luminosity distance that we saw before, measured at redshift z, that you can also obtain directly from the elements. So we can measure both the magnitude and the redshift directly, but we do not know the volumetric magnitude of the element. Another concern that we have is that inside this luminosity distance function, there lies a Hubble, which is also another parameter that we're trying to discover. And due to the way that logarithm works, this Hubble function will be kicked out and will be summed together with the volumetric magnitude, effectively meaning that there's a degeneracy between it. And as we're doing a Bayesian analysis, we have to consider a likelihood. We, in this case, consider a likelihood just a standard partial likelihood of the following form. And because we now know that there are things here that we cannot compute, we have to marginalize the contributions for both the volumetric magnitude and the Hubble constant out, and obtain a likelihood of the following form, where both A, B, and C depend on this delta and sigma, delta is now made of things that we can compute because this H naught cancels the H naught luminosity basis function, and sigma is simply the error for the type A supernova. The moral of this story is that type A supernova cannot constrain the value of the Hubble constant directly. One of the most important pros in cosmology that we have is the cosmic microwave background, which is essentially the first light that has reached us from when the universe became transparent to radiation. It is very useful because it can take the whole cumulative expansion history of the universe into account, and it's able of putting very stringent constraints in it. There are at least two ways that one can use the cosmic microwave background in an observational analysis. We can either go with the full way, which is to simulate the perturbations numerically with specialized codes. There exists two codes that I can think of, for example, plus and down. Or we can use the easy approach, which is to take what are known shift parameters, which take into consideration only the first acoustic peak in the temperature and isotropies of the CMP into account. As you can probably guess, in this work we decided to go with the easy approach, otherwise I would have mentioned it. So in this easy approach, we have what are known the three shift parameters, which are this R, this LA, and omega V, where Z star is simply the redshift for photon decoupling, so the redshift for the CMP. This R is the moving distance with our already familiar Hubble function, and RS is the moving sound horizon, where CS is simply the speed of sound in our fluid as a function of the redshift. Just to have a visual idea on what this looks like, here's the CMP, the image that we usually show as measured by Planck, and here we can see its multiple expansions. And we can see how well does Lambda CDM fit in this data set, which is given by the green line, and you can see how well it can actually constrain our models due to how small the error bars of the CMP are, especially at higher multiples, which corresponds to physically smaller scales. Okay, so with the development of standard of gravitational astronomy, we are able to have a new probe for the study of the cosmos at a large scale, and these probes are known as standard CERN events. So standard CERN events are simply events where we have an emission of both gravitational waves and an electromagnetic field. These events are very interesting to cosmologists because we can actually obtain the luminosity distance for gravitational wave directly and its redshift from its electromagnetic field. This means that we can actually constrain these models directly without requiring any sort of ladder distance calibration, so, which means that they're effectively independent from any other cosmological or astrophysical observation. Additionally, because we expect some of these events to be measured at intermediate redshifts, we can effectively probe new regions of the cosmos which were previously inaccessible to us. Unfortunately, there's only been one standard CERN event so far, which is GW170817. And it's the one that I'm showing here. So instead of using standard CERN catalogs to constrain our cosmological models, because one event is not enough to provide meaningful constraints on the models that we'll be studying, we'll instead forecast the constraints that these standard CERN events are expected to bring us in the future. In this slide, I'll schematically explain how the procedure that we employ to generate such data. So we start by taking the theoretical probability distribution function for each observatory, for observing a standard CERN event for each observatory as a function of the redshift. We then sample this distribution and to obtain a given redshift. Let's represent it schematically by saying that we have obtained the point marked in red, and then we compute the corresponding luminosity distance for that event using a reference cosmology, which in our case we took to be lambda CDM. We then take the expected error as a function of the redshift for the same observatory. We compute the corresponding error for that redshift and consider it to be the one single region around the computed value for the luminosity distance. Then, to obtain a more realistic catalog, we sample a new value of the luminosity distance from a Gaussian distribution. We then repeat this process the number of times equal to the number of events we expect to observe for all observations. To simplify this process, we created a small tool. It's called GW catalog, and if you're interested, it's available in the following GitHub URL. So for which observatories will we perform our forecasts? We have LIGO, LISA, and the Einstein telescope, each of which with their corresponding timescales. Okay, so because we're talking about catalogs and probability distribution functions, we must provide statistical confidence in our results. To do so, we generated 15 different catalogs for Lisa, each with 15 events, and we picked the best, median, and worst catalogs. For us to say what the best, median, and worst catalog is, we rated them based on how small their 1 sigma regions for each parameter were when multiplied. As for the Einstein telescope, we generated 5 different catalogs, each with 1,000 events, which all showed to be similar, so we only considered one catalog. As for LIGO, we generated 15 different catalogs, each with 50 events. However, LIGO wasn't able to set proper forecasts on our models, so we had to consider the best, median, and worst LIGO catalogs, and when based on how well it would complement the worst Lisa catalog. Okay, so because we're effectively interested in telling between our effective cosmological model and what city apart, we must apply some sort of model selection criteria. The model selection criteria that we decided to use is called leave one out cross-validation methods, and I'll be explaining schematically how such a method works in this slide. So we start by taking a dataset with n events, here schematically n is equal to 4, and what we do is we constrain this model using n minus 1 events, and then we attempt to predict the left-out event. We then repeat this process for the other events in our dataset, always doing the same procedure, constraining with n minus 1 and then predicting the last one. And we consider that the model which is best able to account for all left-out events is the best. Unfortunately, because the constraining model n times can be computationally expensive, a procedure which is called Pareto smooth importance sampling was used, whereby making use of the constraint of the model with n events, we constrain the full model with all of the events, we estimate what does this fit look like with n minus 1 events. And
so how are you varying the model? So are you considering particular kind of normal transforms for your functions, say Q or something?
yes,
And with some coefficients and then varying the
exactly. Well,
you'll show us the forms that
exactly. I'll show you the form for that. This is just. But it would be good to show the methods first and then the model. Yes, hopefully it's clear. So we then estimate. We use this procedure to estimate the fits. And then we apply the leave one out cross-validation method as described above. This leads us to obtain what is known as the expected log point-wise density, approximated by the Pareto smooth importance sampling using leave one out cross-validation methods, which we have just shortened to ELPD instead for obvious reasons. Okay, so as I hinted before, we are doing our analysis in Bayesian, right? So in Bayesian statistics, unlike frequency statistics, our parameters are probability distribution functions and not fixed unknown values that we try to discover. In this Bayesian way of thinking, we need 3 things for our analysis. So we need a likelihood, which I already mentioned before, this is the case for the type of supernova, which states the probability of observing a data set X, knowing a set of parameters theta, the data X, obviously we always need the data, and some prior belief on what our parameters should be. Then using Bayes' theorem, we can actually compute the posterior distribution function, which is what we're interested in, which tells us the probability of theta, our parameters, knowing theta. However, because obtaining this posterior distribution function can be computationally expensive, a set of family of methods, which have been developed in the last few decades, which are called Markov-Chain-Monte Carlo methods, were developed, where they sample the posterior distribution in a weighted way, such that they visit regions of high probability the more, and regions of low probability the less, and effectively try to sample from the posterior, try to approximate the posterior distribution using the finite set. There are several algorithms available, implemented in different programming languages. So very shortly, we use the STAN programming language and the hard-disk Python package for exploratory Bayesian analysis and modeling. So I'd like to spend just a few seconds speaking about the STAN programming language. So it's a programming language developed specifically for Bayesian analysis. It is developed by a team of statisticians and programmers, and it has a wide range of interfaces. So you can use it across different programming language, of which I would like to highlight, for example, Python, R, or even directly from your terminal. You can use STAN in all these different interfaces, share it with your coworkers, etc. The language is written in C++, and it comes bundled with a set of pre-optimized math libraries, integrals, ODE solvers, algebraic equation solvers, etc. And it has very good documentation and a whole ecosystem of which RVS is a part. It's the same developing thing. In the beginning, when I started doing my studies, I started with Python-based software. You typically use by cosmologists, so EFCE and ProgrammMC. And moving to STEM was just orders of magnitude faster. And thanks to its very good documentation, I was able to get things started and up and running without much friction. And I knew essentially nothing about vision analysis. So the documentation not only teaches us how the programming language works, but how the theory works, which is very convenient. Okay, so finally, moving on to physics and on to original work. In this part of the presentation, I'll be talking about the most general FQ cosmological model with the luminosity background. So here's the functional form for this FQ cosmological model. You can see that it diverges from GR by an extra term, which includes this parameter alpha, that when set to 0 means that this model will essentially convect to luminosity. Next, we consider a universe that is permeated solely by matter and a cosmological constant, and we're neglecting radiation on the basis that our analysis will be done with low redshift observables. Therefore, we don't expect radiation to play a significant role. I think so.
Well, there are models like that for the Ricci scale, which is not following that. Anyway.
I think so, but I can. I remember very well. If we then insert these assumptions into our modified first experiment equation, we obtain a Hubble function of the following form, which is exactly the same as the Lambda CDF. This is what we mean by a cosmological model with the Lambda CDF. Additionally, as we already know, the propagation of gravitational waves in these models are modified, and here's how it looks for this specific one. Then, because there's a degeneracy between alpha and omega matter, which are 2 of our parameters, we have to do something about it for analysis, and we'll be using type A supernova to fix the value of omega. Okay, so here is the forecast set by Lisa. We can see the corresponding catalogs on the left and the corresponding constraints on the right. If you look on the right, you can see the worst catalog by Lisa, which is in blue, is significantly worse when compared to the median catalog that's measured by Lisa, which is in red. By contrast, the median catalog, which is again in red, and the best Lisa catalog, which is in green, are very similar to each other. If you analyze these plots on the left between E and time, you can actually see a pattern. The best catalog seems to be the one that features more low redshift events, while the worst catalog seems to be the one that features less low redshift events. This makes us believe that there's an optimal region to constrain this model, which is located at low redshift. As for the Einstein telescope, it has 1,000 events, which is enough to closely match the underlying statistical distribution, and that's the reason why we only needed to consider one Einstein telescope. If we put the best Lisa catalog and the single Einstein telescope catalog side by side, you can see that the best Einstein telescope catalog, which is in red, can actually beat the best Lisa catalog. This is surprising because Lisa's maximum redshift range is about 3 times larger than that of the Einstein telescope, meaning that studying high redshift events is not a requirement to constrain this model. However, even with only 15 events, Lisa is able to compete against 1,000 Einstein telescope events by providing only slightly worse constraints. Okay, as for LIGO, as I already mentioned before, it is not able to provide any meaningful constraints by itself, so we have had the worst Lisa catalog in Lisa. You can see that there's still quite a bit of improvement by considering data from LIGO. We can see here in blue, there's the worst Lisa catalog, and when we then add data from LIGO, we can actually obtain significantly smaller catalogs. This means that if in the future we are unlucky enough to observe a bad Lisa catalog, then we can rely on data from LIGO to improve the quality of the constraint. To understand why LIGO alone isn't able to constrain our model, we have zoomed in the low redshift regime. Here you can see that the error bars from LIGO, which is in red, are just massive when compared to those of the Einstein telescope, which is in green. And the error bars from Lisa, which is in blue, aren't even visible at this time. This is the reason why LIGO alone will not be able to constrain our model. And this is also the reason why 15 events by Lisa can actually compete against 1,000 Einstein telescope events, assuming that they are on the right place. Hence, the massive statistical fluctuation that Lisa has in its counts. Yeah, because the error bars are really small on Lisa, if you land on the right place, you're good. But if you go to higher redshifts, the error bars become larger, and the distinction between the was not as clear, so please become less effective. Because essentially we saw that there's an optimal region to constrain this model. It's not general across all models, obviously different functional forms lead to different behavior. But essentially this was the region where there was like optimal constraint power.
Low redshift region, since it's so precise.
Yes, it could beat or at least compete against 1000 access. Okay, so here we have a summary of the one sigma regions for the parameter alpha for the more random cases. I don't show the one sigma region for all geometry because it's fixed by that one supermodel, so therefore it's the same for all catalogs or for all combinations. And the one sigma region for the whole constant was approximately linear. And then we can see here what I've just said so far. So yes, the telescope is the best case scenario. This is the best. We can provide us with the smaller error bars. The best Lisa catalog is about 50% larger. And due to its massive statistical fluctuation, the worst Lisa catalog can be almost 7 times worse. We can then improve that significantly by using LIGO that can actually approximate it to a median Lisa catalog. Okay, so to the second and last model in this presentation, I will present to you the study of an effective cosmological model that does not include dark energy, but is still able to account for the accelerated expansion of the universe. So essentially, we're trying to replace dark energy. Okay, so here's the functional form for this model. We can see that it deviates from GR by an extra exponential term. This extra exponential term has the lambda, which is not a free parameter like the previous alpha, because it can be related with the energy matter content of the elements. If
That's Q naught over Q in the exponent.
exactly,
So it's a 1 over Q in the exponent.
exactly.
So it's not analytic or near Q equals to 0.
Sorry,
It's not analytic near Q equals to 0.
exactly.
Is near Q equals to 0 the Newtonian view?
It's Minkowski.
It's Minkowski.
Exactly.
So does this give you a kind of Newtonian gravity in the small?
We saw that it goes. It is actually one of the last issues that we were debating, and that was one of the questions of the referees, and that was something.
I was aware.
Yeah, what happened? Excellent.
No, I was not.
I know.
Did you sort it out or?
We see that for Q equals to 0, it's not defined, but Q not also goes to 0. So it has an positive limit. It cannot do it for Q equals to 0, but it's a limit.
You need the Q not go to 0.
The Q not goes to 0. Is the non-metricity scalar evaluation today, which can be the equation we have Q equal to 6h squared. So Q naught will be simply 6h naught squared. So it's the double constant.
That's far from the other point is parameter. It's a fixed parameter. This you put in the Lagrange, right?
The Q naught.
The f of 2.
The f of Q is the functional form that
You put in the Lagrange.
you can put whatever.
Right. So that lambda and that Q naught are constants that you put in this.
The Q naught is simply in this case for the flat color double metric, it's simply 6h naught squared.
Right. That's how you interpret it. But when you put it in the Lagrangian, so Q naught is a constant.
Yes.
Yeah. Okay. So you cannot put it to 0. It's a constant.
But it's okay. Probably not necessarily it's a constant because it also goes to 0. Let me think. I remember that in our final statement, we agreed that we find Minkowski as a limit, not necessarily as a
Specify.
yes. Maybe I should probably check that. Okay, then I'll speed it up. Okay, so we insert this model into the modified Friedman equation, and now we consider a universe that is permeated only by matter and radiation. We obtain the closed system of the following form, where x1 is related to the evolution of the matter density, x2 is related to the evolution of radiation density, and x3 is related to the evolution of the parameter lambda. A very important note to take is that if we set lambda equal to 0, although we have Q, it does not mean that we have GR. Sorry, lambda sphere. Although we have GR because f equals Q, this model does not include dark energy. Therefore, it's not a lambda CDM model, or rather a simply CDM model. cosmological model without the cosmological constant. Because we have a closed system, in order to study its properties, all we need is to study two of its variables, of which we pick x1 and x2. And we've differentiated with respect to the number of equals, where the number of equals is simply defined as the logarithm of the scale factor. It's a proxy for time in this dynamical system. There's an interesting symmetry between x1 prime and x2 prime, which is the only difference between them is 3, which comes from the scaling of matter, to a 4, which comes from the scaling of radiation. So it's the only difference between x1 prime and x2 prime. In this plot, you can see the dynamics of the system in phase space, its corresponding fixed points, and the existence of 3 disjoint regions based on the sign of lambda. So if you start from the bottom left in the light blue region, we have the case where lambda is greater than 0. We can see that it includes our only stable fixed point, which mathematically corresponds to a lambda-dominated regime. Physically, it means a universe in accelerated expansion, or the one that we observed today. In between the two blue regions, we have the orange region, which corresponds to the case where lambda is equal to 0. And we can see that the trajectories flow from the unstable node, which corresponds to the radiation-dominated epoch, all the way to a deceleral node, which corresponds to matter-dominated epoch. As for the blue region in dark blue, it corresponds to the case where lambda is smaller than 0. All trajectories diverge toward infinity, meaning that our universe will eventually go to epoch. This means that in order to agree with the evidence that we have of an expanding universe, our value of lambda must be strictly positive and our universe somewhere right here. And where it begins in a radiation-dominated epoch, flows all the way to matter-dominated epoch, and ends up in neural inflation, which is our current state. Then we try to see whether we can actually make a distinction between these two models using standard Saran events. So here's the luminosity distance for gravitational waves for this particular model. On the left, you can see the corresponding best fit curves for both on the CDM and this model of Q with the Einstein telescope. And on the right, you can see the ELPD for the Einstein telescope and the best laser catalog. So the non-selection criteria that I previously discussed. To the proximity of the best fit curves and the proximity of the values of the LPD, we can easily conclude that the standard Saran events will not be able to tell between this model of Q and lambda CDM apart. So no model is preferred over the other. We then try to assess whether by increasing the number of catalogs, we can actually make a distinction between them. So we generated several catalogs with an increasing number of catalogs. We computed the average ELPD across all catalogs. And what we saw for Lisa is that no matter how many events per catalogs we have, no distinction between the two categories. Models are equally good. For the Einstein telescope, the same procedure was applied, only with an even larger number of events per catalog. And once again, no distinction between the two. This makes us believe that when it comes to standard Sarans, this model of Q is able of perfectly replicating the dynamics of lambda CDM, which is good. Then we try to assess whether that one is supernova could actually be able to make a distinction. So then we use type 1 supernova from the Pentane sample. Once again, on the left, we have the best fit curves for both on the CDM and this model of Q, and on the right, the corresponding ELPD. Once again, just like in the previous case, no distinction between the two models can be made, which means that this model of Q is also perfectly well of replicating the dynamics of that one supernova in electricity. However, when we consider both of them together, the tension arises. So if we see on the left, you can actually see the constraints set in lambda CDM by the standard Sarans and type 1a supernova. When you consider the standard Saran events, which we created using lambda CDM, we have these 3 blobs right here. And when you consider type 1a supernova, which we already know agree with the lambda CDM universe, you can see that there's an overlap. So there's an agreement. However, if we move on to the f of Q, we can see that there is a tension in between them. This effectively means that if our universe can in fact be modeled by lambda CDM, then it is expected that the future gravitational wave observatories will create a tension in this model and effectively rule it out. However, the sad news was that all of this was in vain, because even with current data, so both type 1a supernova and the CMB, there's already a tension in this model. So as you can see, here there are constraints set by type 1a supernova and the constraints set by the CMB. This takes place because if you look at the modified first Friedmann equation, which takes a for this model, and you make a high redshift approximation, you can see that the Hubble function without the Hubble constant, which is how we define E, is essentially lambda CDF, where small lambda is playing the role of the cosmological. However, if you are working in low redshift regimes, this is not the case. You can actually see that the abundances are corrected by an extra exponential term, which depends on lambda. And now our cosmological constant is essentially 2. This causes a mismatch between the low and high redshift regime, which is only visible when we actually use data sets from different ends, which is the case with the CMB and Taiwan super. We can actually constrain this model with cosmic with other low redshift observables, such as cosmic chronometers, redshift space distortion, or variant acoustic constellations, and they will all agree with Taiwan. The only reason why these other stars did not agree with Taiwan supernova was because they have effectively a modification in their propagation to that extra term that has been carried with us throughout this presentation. And so, to conclude this presentation, with a brief summary of the original work, we've constructed standard thermal catalogs from LIGO, LISA, and the Einstein telescope. We studied the most general FFP cosmological model that replicates the lambda CDM vector, and we saw that it introduces one additional pre-parameter model. We also saw that the Einstein telescope will outperform LISA, and that LIGO alone will not be able to constrain this model. We saw that LISA and LIGO are subject to non-negligible statistical fluctuations in their catalogs, while the Einstein telescope is not. This is due to the number of events that the Einstein telescope is expected to observe, and that LIGO will be able to improve the quality of the constraints set by LISA. We then studied the most an FFQ model, which replicates the late time expression of the universe without dark energy. And we saw that it introduced no additional pre-parameters, and that neither standard Fermi events nor type 1a supernova are expected to distinguish between this model and lambda CDM on their own. Unfortunately, there's a tension between type 1a supernova and the CMP effectively ruling this model out. And with this, I finished my presentation. Thank you for listening and questions. Questions? Just to answer. It's this URL. It was made originally by Tessa Baker and then by I don't know, and then posted on this website in a very beautiful way.
Yeah, I've seen other versions, but not exactly the distribution that well. Well, yeah, so you use two different models, right? For the you have a square root one and then an exponential one. Of course, one of the easy criticisms about this one is right? But I was wondering why in the two analysis you actually decided to use two models. I mean, at least if you kind of decided I'm going to use this particular, why not? Yes, not pick one and then rather use two different ones.
That is a good question, and I should have probably motivated the functional form. So the first model was shown to alleviate this tension on the sphere model. So it was promising, and our goal in that were previously by my supervisors, and our goal initially was based on this model was promising. What can actually future concern of itself about it? Will they be able to constrain it? Will they not be able to constrain it? So our line of work is essentially that. Can future gravitational wave observatories actually tell that this model is better than on sphere because they already have this bunch of other possibilities? So that was the motivation for the work. And then the study in this second model showed that the literature where it was able of replacing dark energy entirely, and in the first paper where this model was presented, they only used low redshift observables, and so it seemed that they were able to replicate the dynamics of the CDM universe without dark energy, and that's why we started studying this second one. So there are more practical reasons than rather other theoretical reasons.
Anyone?
Of these models, the FQs, FRs. I mean, if you put enough terms and their associated parameters, can you fit this model to any kind of physical observation?
Yeah, probably.
Okay, so but that there's no I mean, power with the powers. And whatever you can find it.
You can keep adding.
Yeah,
Why not?
yes. Okay.
But that's, I mean, the limits of theory is the limits of our imagination. You can just keep putting the stuff there.
Okay, but then it doesn't predict or explain anything.
It can predict, because you can constrain it, and you predict whether the
Yeah,
prediction.
but can it explain anything? Because so
Can you provide some meaningful, sorry, can you provide some meaningful physical insight? Maybe not. I don't know. It depends on the situation. Once again, it's probably the discussion that we started early on, right? What's the physical interpretation of most of these things?
and I have another question as well about the non-metricity. For example, curvature and torsion, we can imagine it quite easily, even without a metric present. But non-metricity, how does it work? What happens to geodesics? What do you say?
I can answer that for sure. I can answer that. Okay. So yeah, that's one of the things that also has bothered me since the beginning, right? Because we're working on characterization at the cosmological scale. And that's easy because we have an ecological in the background, so things become much simpler. Now we don't have to deal with all of the jungle. We have this simple modified Friedman equation and some modifications at the perturbative level. So we just have to take that into account, look at the observables, perform statistical analysis, and actually see whether that brings us somewhere closer to what we wanted right now. But this is completely, I mean, phenomenological, right? So we don't understand dark energy. We now have a theoretical framework that allows us to say what our function part that we want.
Yeah, but even geometrically
Yes.
speaking, what happens? I mean, take a curve with torsion, it goes into a nearest, for example. But what happens? What is non-metricity exactly?
It's, yeah.
Yeah, there is no, I don't know, even in lower dimension geometric curve example.
Probably, but not that obvious.
Question, it's along the lines of second question. Isn't there an organizing principle or someone thinking about it to motivate this function, this effort, or in like for example some symmetry or something that could define what are acceptable functional traits of this field, or is it completely arbitrary by any means?
There are some guiding principles. I remember reading something about, probably everyone else more there than I am, but I remember with FFR theories, people linking things are additional goals. I remember seeing that phrase quite often in some models, and they are that issues or fundamental issues with some our models, which I imagine in FQ will be exactly the same. So that whatever there, obviously you're going to get confidence. And so there has to be some sort of motivation for the things that we do. But in practice,
Cosmological.
but they're more
Formal.
you can obviously insert that when you're making your model so that it makes some sense. If I just start putting sort of there, people will most likely it will be more in the actual consequences because it doesn't make theoretical sense. Obviously, it's not just throwing stuff up, but there is situations where you can do that. I remember seeing people that were working on parameterizations using lots of terms and then kind of trying to work out what would be the function that would actually replicate this thing. Yes, that's some philosophical issues of getting to explain because it might be that just selling terms. Obviously, different people think of it differently.
So, one also question of calculating.
The point is that there is quite a number of modified theories, right? You show the picture there. So I assume people have sort of tried to do this analysis with also in other theories or similar with looking at exotic matter, or whatever they want to describe these effects. So has this analysis been compared sort of to other analysis people have done, or as far as you're aware?
In what sense?
I mean, if people have tried to do similar analysis to try to explain
To other theories of gravity.
yes.
Yes. So if you reference about the power, there's so many, for example. If you want, there's a very large review on FFT, and because it's an angular public record, then it's exactly the same. People, there are few things in our web, not all of them, that make reviews on this quantified theories of gravity, so they'll just sometimes out. But I'm only aware of the work that has been done mostly in motion scales. For example, I don't
Yeah, I was
focusing
on
at an astrophysical level.
yeah, I was focusing more on the cosmological
Yes.
scale.
But on cosmological scales, yes, there are views that include gravity and not only modified theories of gravity.
Yeah, I guess another way to interpret my question would be why exactly is this model? I mean, if there was like a priori principle, or did you, or it was more like let's try this model and then see the results and it
Yes.
okay. All right. So I guess it's time. So let's thank again the speaker.